The machine you're making is Pumuaishi version 2. It's a ventilator that is supposed to help someone breathe or breathe for him. So we came together and agreed that this is a circuit we need, and everything is documented in this large file. The biomedical gives us what is required on a patient machine and what we expect as the outcome. And after which we come now and sit here. My part is programming the board, and the code we had to benchmark from Israeli, and we had to benchmark also from the USA, so that we may meet the universal standard.
Right there on after the programming, then what follows?
After programming, then I test my code on a circuit.
For a layman, what's the importance of a circuit?
The importance of a circuit basically, these parameters are quite sensitive and you need to get them right. So the circuit has to be well filtered, well calibrated, such that so that you can get your parameters right. Again, these are an equipment that will be used to treat people, so we need to get the parameters right. We have no other way around it. So a circuit is very, very important in this process.
In the event that it's not gotten right, what are the repercussions for the user?
So this way, see, we began with a small motor. Just look at it. So the first test was this with a basic motor driver, and we realized it's misbehaving, it's overheating, can blow up. We moved to another step, we moved to another type of motor with this driver, and we realized it's also heating up. So it has been a process of testing, failing. He has had to change the board several times. Yes, you can see the work that the mechanical team has done. All this was their work, all this design. All this was their work. And our bit of electrical and programming is all covered in this board. Yes. This is
all the circuit and the codes are all now assembled in here.
Yeah. This board is going to be very summarized in the end. The end product will be very small. Yeah, it's supposed to be half the size of this. You see the part of the clinical, all these circuits and their standard, the filters, the lung, the sensors, how much volume we are going to press this bag. The medical team came in there.
What does what in this scenario?
Basically, this machine utilizes the principle that every time in a hospital setting, if a ventilator fails, or if they're transporting a patient from one place to the other, they use this ambi bag to manually ventilate. So what the machine is doing is mechanically do that ventilation. So how it works, we have a source of oxygen. This is an oxygen concentrator. It makes oxygen from the air, goes into the bag. Our bag in this case is a compressor. It's like this. This is how a standard one looks like that. So you ventilate the patient. So the oxygen goes to the bag. They call a BVM.
Is there any specific amount of air that is contained in here?
Yes, no, that's why we have an equipment, because depending on how far you compress, it determines how much volume you give. So it's a calculated value, and these two arms can give a percentage of how much they've compressed to the patient. So you get our oxygen here into the bag. Then from the bag we have a filter. This is a viral and bacterial filter. This is to protect the patients because it's aspirating air from ambient air. So in the event there is anything in the air, it's filtered here before going to the patient. And then we have the first protection. It's a mechanical protection valve. Remember, some patients have stiff lungs. So if there is a restriction, instead of causing trauma to the lungs, it relieves the air from this point. So it's a safety mechanism. Then from there, through the tubings, goes to the patient. So in our case, our patient is this. This is like a lung. This is a test lung. Yeah? So it delivers the gas to the lung. And then that is only during when it's compressed. So when the patient is exhaling, There is a valve here. This is a valve. It closes when you are pushing air in. When you are exhaling, it opens through another viral filter, in this case, so that the one patient cannot cause infection to other people, and then exhales it to the air. At the end here, there is a gadget. We call it a PEEP device. We don't want to remove all the pressure from the lungs, so that's why it leaves it. It controls the amount of pressure that's going to remain in the lungs. That's why it's a PEEP valve, PEEP, positive end expiratory pressure. And then from the patient point, here, I forgot to say, we have a filter. We call it a heat moisture exchanger.
Yeah, like 3 filters in one pipe.
Different function. So this one protects anything from outside to the patient. This prevents moisture loss from the patient, and also whatever the patient is exhaling, it filters most of it. That's why we call a heat moisture exchanger. And also protects, we have an oxygen sensor. You see there's a white, sorry, I don't know whether you can see. There's an oxygen sensor there. Measures the amount of oxygen you're giving to the patient. And then there's a last filter there that protects now us, the caregivers.
What's the difference between this one and the other that we've been seeing in different hospitals? Because this one is locally assembled. What's the major difference?
The major difference is that it's a standalone device. It's a low flow device. You can
Say low flow. What's the meaning of that?
You see now we are getting oxygen from a concentrator. From other ventilators, you have to get oxygen from a cylinder. All right. So this can be used in a local setting where you don't have oxygen, and you can just, or in an isolation setup. You see where they just make a hospital, they can just push it in, plug to power, and it starts functioning. It is electric with a battery backup.
It has to be charged.
Yes. So in the event you take it to a place and there's no power, you can still ventilate for 4 hours as you wait the power or the guys sort of the power issues.
How long does it take to come up with a complete machine?
The prototype took quite long, but from
2 weeks
took 2 weeks.
to assemble everything and have the idea in line.
Yes, to
But
make
per
it
day,
like,
per day we can make a production 100 per day.
Talk about the cost, because most people would want to know, well, it's assembled in Kenya. Is it affordable?
Yeah, it's very affordable. A proper ventilator which is imported from outside the country would cost about 2.5 million to 5 million shillings. Our ventilator, which we've designed locally, would cost about $6,000. So that's 600,000 shillings. So I think it's about quarter of the price of what we would actually import. And 75% of the materials are actually manufactured locally.
What's the capacity? How much are you able to produce?
After two to 3 weeks, we should be able to do 100 a day, and we can also scale up to 200 a day, as we have enough capacity within the automotive sector in Kenya to service the region. So we're looking at about anywhere between 2,000 pieces to 4,000 pieces a month. Yeah.
Would you say this is purely Kenyan made?
Yeah, I would say that this is clearly Kenyan made and made by Kenyans. We have a lot of talent in Kenya, and I think this is a start to a lot of new innovation we have to do in Kenya.
What's been the most challenging part or the moment in coming up with this machine?
I think very early on, in the early days, we just built a simple machine for compressing a resuscitation bag. And that's not really what a ventilator is. It's when we actually realized the complexity of a ventilator. It was suddenly like looking at, you thought you were up the mountain and then you looked up and you saw a huge cliff. And I think overcoming that, all those specifications that are required for a ventilator, in the early days that looked insurmountable. But as we brought more and more people into the team to deal with all the different elements and aspects, those things have disappeared over the last few weeks.
Probably, what do you foresee in the future when it comes to this?
Well, I think one of the largest things that's come out of it for us has been what we can achieve here and the price point we can achieve. Yeah? We're doing this in an enormously fast timeline, and we're looking to undercut imported goods by about 80% of cost. Yeah, I'm sure this is possible on many, many other life-saving devices in the medical field.